Okay, so this is part 2 of chapter 6, section 2. So here we're still using u substitution, but here we're going to do substitution in definite integrals. Okay, so a defined integral. To evaluate a definite integral by substitution, you substitute u, letting u be g of x, and of course du being the derivative of g of x times dx. And then integrate with respect to u from u equals g of a to u equals g of b. Now a and b are your lower and upper bounds. So I'll explain that method. This is basically using the fundamental theorem of calculus method. There are two methods for solving a defined integral using u substitution. I'm going to show you first method 2. This right here is known as the fundamental theorem of calculus method, which actually is going to be easier, but I am going to show you both methods. Okay? So method 2, basically method 1 being an undefined integral, method 2 being using u substitution for a defined integral. On the exam, of course, you can choose which method you're going to use. And the thing is with definite integrals is you cannot back check. Okay, you cannot check a definite integral. Your answer is going to be your final answer, and there's no way to see if you did it correctly or not by finding the derivative. Alright, so here we're going to make a u substitution and integrate from u of a to u of b for the following integral. So first, basically, I'm gonna show you guys the fundamental theorem of calculus method, which is what this says. So I'll explain what all this means while doing this method. So you start off with the same integral setup. So that means you're still going to choose a u, and in this case u we're going to pick as 1 minus x squared, and then du is going to be negative 2x dx. Now keep in mind that basically we want to replace the x dx, so that means this negative 2 needs to move over. So we're going to divide both sides by negative 2. So then du over negative 2 is equal to x dx. So now that we figured that out, we can rewrite our integral as the integral from 0 to 1 of u times negative 1/2, right, or 1 over negative 2, whatever you want to say. So 1 over negative 2, if that makes it simpler to see, du. Okay, so we replaced the x dx with this, and we replaced the, I'm sorry, and this is supposed to be square root of u, my bad. So square root of the inside, which is square root of u. So now, of course, this is where the fundamental theorem of calculus comes into play. So here, we're going to recalculate the limits of integration. We're going to recalculate the limits of integration using the bounds. So basically what that means is we're going to say, all right, u of the upper bound is 1. What is u of 1? So that means we're going to take 1 and we're going to plug it into our u that we chose. So in this case, it's going to be 1 minus 1 squared, which is 0. And then u of 0 is going to be 1 minus 0 squared, which is 1. So by using by recalculating the limits of integration, what we can basically do now is we can change limits in order when we put in u and du. We can change our bounds or our limits. We can change the limits in order. They have to go in the correct spot, and use our u, du, and du. So basically our new integral is going to look like this. I'm going to use this integral right here, but now instead of my bound of 1, I'm going to replace it with 0, and instead of my bound of 0, I'm going to replace it with 1. By doing this, then all I have to do is integrate square root of u times 1 over negative 2 du. So I don't have to go back and substitute in whatever u was. So let's continue integrating this. So I'll take my negative 1/2, of course, and bring it out. So this becomes negative 1/2 of the integral 1 to 0 of square root of u du. And we know the integral of the square root of u is u to the 3/2 divided by 3/2 plus c. But remember, this is defined. So now we're going to define this from 1 to 0. Rewrite this. So you take the bottom guy, right? Flip them and multiply. So we end up with negative 1/2 times 2 over 3 u to the 3/2. Remember, the plus c in a definite integral doesn't matter because it ends up canceling itself out. So I'm just going to ignore it from now on. Alright, so negative 1/2 times 2/3 is going to be negative 1/3 of u to the 3/2 from 0 to 1. So since I'm using the fundamental theorem of calculus, I'm using my new bounds, my u bounds, then there's no need to back substitute. So here, there's no need to back sub, which means I don't have to plug in what my u is. I can just integrate it from right over here. Okay? So why do we not have a need to back sub? Because what we did is we changed our u's. We changed our limits. Okay, so now all I gotta do is put negative 1/3, plug in 0, minus negative 1/3, plug in 1, and we get negative 1/3. Oops, sorry, that is actually ends up 0. So this becomes positive 1/3 times 1, which is just 1/3. So that's using the fundamental theorem of calculus. Okay. Now method 2 is exactly what we've been doing. Okay. So it's using the u, figuring out our integral. So it's starting at this step right here. So starting at this step, and now just integrating like we always have done. So take out the 1/2, so negative 1/2 of the square root of 1 to 0. See, I'm not changing anything. I'm going to integrate this with these bounds. So I'm not changing my limits. I'm not changing my upper and my lower bounds using my u. So that means I have to back substitute. Alright, so we know that this the integral of square root of u is u to the 3/2 over 3/2, which we now know is the same thing as 2/3 to the 3/2. And if you're wondering what I'm doing, just go back to this step right here. It's the same exact step. Plus c from 1 to 0. The 2's cancel out, so we have -1/2 u to the 3/2. Remember, because this is a defined integral, I'm going to ignore my plus c. Alright, here I'm going to back substitute. So it's -1/3. What was my u again? 1 minus x squared from 1 to 0. So now plug in the 1. So -1/3, 1 minus 1 squared, which is 1, minus -1/3, 1 minus 0. Remember, this is squared and this is squared, just in case you guys, that confuses you. So here, -1/3, 1 minus 1 is 0, so that actually ends up canceling out. And here we have 1 minus 0, which is 1, times -1/3. Of course, distributing the negative, so it's 1/3. So you get the same exact answer both ways. You choose which one you want to do on the exam. On the AP exam, they may ask you to use the fundamental theorem of calculus to do this. Okay, so it's probably very beneficial to know both. I personally think that this is the easier way, okay, using the fundamental theorem of calculus, because there's no need to back substitute. Just change your limits and use the u. Change your u's, use the u's. Okay? So in class, after you're done watching this video, you're going to pause it and you're going to work on these problems. Okay? You're going to use, I want you to use half using the fundamental theorem of calculus, and half of them use the method 2. Okay, that we've learned, the u substitution and then integrating in there. Alright, since you guys are doing this with the sub, I did making a newer video, so I'm adding this next page. But this is not hard. This is separable differential equations, which is basically the step in the initial value problems that we were doing. This just says that a differential equation, y prime equals fx y, is separable if f can be expressed as a product of the function of x and a function of y. The differential form equation then has this form. So basically the idea is that if h of y is not 0, because you have to have an x and a y, you can't just have one or the other. We can separate the variables by dividing both sides of the equation by h of y, obtaining in succession the following. So first get all of your, so what basically the idea is separate the y stuff from the x stuff. Exactly what we were doing for the initial value problems. So get your h of y's with your dy's and your h of x's with your dx's. So that way you can integrate them. So here, once your h of y is with your dy and once your d of x is with your dx, you can integrate both sides. With x and y now separated, the integrated equation provides the solution we seek by expressing y either explicitly or implicitly as a function of x, up to an arbitrary constant. So let's start this problem. So here you have the derivative is this. We basically want to be able to solve it for a set constant, whether it be y or x. Now in this case we want to solve for y. So step 1 is we're going to separate. So let's get our x's with our dx and our y's with our dy's. So here, this guy right here has an x, and here's an x. So that has to get together with the dx. So the first thing I'm going to do, and all of this is multiplication. So the first thing I'm going to do is I'm going to multiply both sides by dx. So we get dy equals 2x times 1 plus y squared times e to the x squared. So all of this stuff gets multiplied by dx. Now since this is all multiplication, I really don't need these parentheses, but whatever, I put them there to begin with. So now the only part that has a y in it is this part right here. So I'm going to divide this whole entire thing by 1 plus y squared on both sides. So the 1 plus y squared is gone. See, I can't divide by y squared by itself because there's a plus right there. Okay? If there was no plus, then I could have just divided by y squared. So now we end up with 1 over 1 plus y squared dy equals 2x e to the x squared dx. So after we've separated the x's from the y's, we are going to integrate. And the reason we're doing this is so we can go back. Basically, we're trying to find the antiderivative in terms of y. So this is an implicit equation, and we are trying to find it in terms of y. So we're going to integrate. Now, this right here, the integral of 1 over 1 plus y squared, I'll give you guys a second to figure that out. But this is from the YARF that could be coming very, very soon, so make sure you know your integrals. But this is the integral of this is basically inverse tangent of y. Okay. Okay. And this equals, how do we find the integral of this? Here we're going to use u substitution. So what do you want u to equal? I'm going to just write it in right here. We're going to let u equal x squared, because then that way du can be 2x dx, which is kind of what I see right here, 2x dx. And then u being x squared, we're going to be left with just e to the u. So by using this, there's no reason for me to manipulate this at all. This is going to become the integral of e to the u du. Okay, and what is the derivative? Actually, here, let me just write it in right here. So the integral of e to the u du. So we've already integrated this side, so that's just going to come down. So what is the integral of e to the u du? I'll give you guys a second. It's just e to the u plus c. Okay? And now, what do we have to do? Is basically remember the super constant. Okay? So right here, all we have to do now is sub back in, sub u back in. So we get inverse tangent of y equals e to the x squared plus c. Okay, and that's my super constant. Next step, get a y equals equation. So now what we want to do is we want to get a y equals equation. But how the heck do we get this y by itself? Alright, so remember, this is inverse tangent. So if I take the tangent of an inverse tangent, and of course what I do to one side, I have to do to the other side. So in here I have to take the tangent of e to the x squared plus c. What happens to the inverse tangent? It basically cancels out. So this is going back to trig. Okay, so here we got y equals tangent of e to the x squared plus c. Now this is not an initial value problem, so we do not have an initial condition. We were just asked to solve basically a separable differential equation. Now if they would have given us an initial condition, we could have solved for c, but no initial condition, so we cannot solve for c. Okay, we're going to stop here. I think that's going to be enough. Your homework in class after you're done is going to be those 6 problems. And I want you guys to start on the bookwork from section 2, which is right here, 1 through 27 odd. Okay? So you've already done the phase 1 student practice. Actually, you're going to do the phase 1 worksheet 2 practice. I showed you guys that. And then start the 1 through 27 odd. Alright, enjoy.